Hi, this is Mrs. Murat with some homework help over Unit 2, Lesson 17, pages 191 to 193, numbers 1 through 3, and 5 through 7. So these are in your textbook, and we'll just get started. Number 1, Jada is planning a kayak trip. She finds an expression for the time, T of S, in hours it takes her to paddle 10 kilometers upstream in terms of S, the speed of the current in kilometers per hour. This is the graph Jada gets if she allows S to take on any value between 0 and 7.5. So on this graph, the y-axis is for time, and the x-axis is for the speed of the current. So she's in a river, and the current in the river will go at different speeds. So this is S for speed. All right. So what would be a more appropriate domain for Jada to use instead? So she has 0 to 7.5. But notice there's a vertical asymptote right here at x equals 5.5. And then after that, this part of the graph is all in the negative. Well, that doesn't really make sense for time. So I would say a more appropriate domain, remembering that the domain is the x values, would go from 0 right up to this vertical asymptote. So I would say 0 is less than S is less than 5.5. And then for part B, what is the approximate speed of the current if her trip takes 6 hours? So here's 6 on the y-axis, 6 for the time. Follow it over, intercepts the graph right here. And I would say it's approximately 3.8. And those are kilometers per hour. All right, on number 2, it says a cylindrical can needs to have a volume of 6 cubic inches. A label is to go around the side of the can. The function S of R equals 12 divided by R gives the area of the label in square inches, where R is the radius of the can in inches. And so we have 2 questions. One, as R gets closer and closer to 0, what does the behavior of the function tell you about the situation? And then as R gets larger and larger, what does the end behavior of the function tell you about the situation? So if we were to graph this in Desmos, I would have to use y and x. So y equals 12 divided by x. And I can see now that, as the radius gets closer and closer to 0, it's in this direction. And as it gets larger and larger, that's in that direction. Okay, so a quick sketch of the graph. It looks like this, pretty much, where this is R for radius, and this is on the y-axis, S of R, so the surface area. Okay, there's also a piece of the graph that looks like this. In context, this part doesn't really make any sense. So the first question is asking, as the radius gets smaller and smaller, well, notice the surface area gets very, very large. Okay, so as the radius gets closer to 0, the surface area, or area of the label, gets larger and larger. And then the second part of the question is asking about in the other direction. As the radius gets larger and larger, what's happening to the surface area or the area of the label is it is getting smaller and smaller and actually approaching, but not reaching, 0. So I'll say as R gets larger and larger, the surface area of the label gets smaller and smaller, approaching 0. Okay, let's look at number 3. So number 3 says, what is the equation of the vertical asymptote for the graph of the rational function g of x equals 6 divided by x minus 1? So remembering vertical asymptote, that vocabulary word we talked about in class today, they occur anywhere where the function is going to be undefined. And a rational function will be undefined for any value of x, which will make the denominator of a fraction equal to 0. So we can take the x minus 1 and say, well, what makes x minus 1 equal to 0? Well, x equals 1 would make that equal to 0, so the function would be undefined there, creating this vertical asymptote. So it is answer choice A. Okay, on number 5, the polynomial function. Is this the graph of g of x equals negative x squared times x minus 2, or h of x equals x squared times x minus 2? Okay, so I noticed that part of these functions are exactly the same. The x squared times x minus 2. And so what that tells me is that there would be a 0 at x equals 0. And because of the fact that it has a multiplicity of 2 in both examples, it would create a bounce. Okay? And then also they both contain the factor x minus 2, which means there's another 0 at x equals 2. And so the graph shows the bounce at 0 and that it passes through at x equals 2. The only difference is this has a negative leading term and this has a positive leading term. So the end behavior we're looking at here is, well, as x gets larger in the negative direction, y is getting larger in the positive direction. And as x is getting larger in the positive direction, y is getting larger in the negative direction. So this is showing end behavior for an odd negative polynomial. These are both odd degrees, degrees of 3, but this is the one that is negative. So this is the graph g of x, which is negative x squared times x minus 2. Okay, so let's look at number 6. Number 6 kind of pulls in a lot of prior learning. It says a 6-ounce cylindrical can of tomato paste needs to have a volume of 178 cubic centimeters. The current can design has a radius of 2.75 centimeters and a height of 7.5 centimeters. Use graphing technology to find a cylindrical design that would have less surface area So each can use less metal. So what I know about the current design is that it has this volume, and the new can needs to have that same volume. But currently there's a radius of 2.75 and a height of 7.5. So the first thing I want to know is, what is the surface area of the current can? Okay, so the surface area, remember that little formula, surface area equals 2 pi times the radius squared, so 2.75 squared, and then plus 2 pi times the radius times the height. Okay, and so when I plug that all into my calculator, I get approximately 177, and then these would be square centimeters. Okay, so now that I know the current surface area, now I can find, or attempt to find, a surface area that's going to be smaller than this. So the dimensions of a can with a surface area that will be smaller than this. Okay, so to do that, we're going to use the formula that we came up with the other day last week, and it was the one that uses compare surface area with radius of a known volume. Okay, so that one is surface area equals 2 pi times the radius squared plus 2 times the volume, so 2 times 178 divided by the radius. Okay, so I am going to graph this surface area in Desmos. And then I'm also going to graph this in Desmos as well. So let's do both. Okay, and I'll kind of zoom in here so we can see it really well. Okay, so again, we always have to use X and Y. So Y equals 2 pi times X squared plus, and then this is going to be a fraction. So on the top, 2 times 178, and on the bottom is the other X. So Y is the surface area, and X is the radius, and this is the volume that the can needs to be. So I want to do a second equation because I know the current can design has a surface area of 177, and we're trying to get smaller. So I'm going to see, where does that happen? So Y equals 177. Okay, now I'm going to change my tools here. I know this has a radius of 2.75, so I'm going to have X just go from 0 to 5. And then knowing this is 177, I'm going to have Y go from 0 to, let's say, 190. I should be able to see in that window. Okay, so here it is. So I had to go up. So here would be like 0, 0. But it takes a little time to get all the way up and be able to see that part of the function up there. Okay, so there it is. And here's the little piece we're trying to figure out. Okay, so right here is like, well, where do they intersect? Okay, so this 2.74 and this 3.37. And so notice that for radius values between them, is going to give us a smaller surface area. So the question is just asking us to pick one value between them. And so this is at 3 here on the x-axis. I can travel it up and I see, oh, when x is 3, it's a little bit smaller. So I know this is the actual minimum value, but I like whole numbers. So since we only have to pick one, I'm going to choose a radius of 3. So again, this is the this is the surface area of the current can, and then it can get smaller until there. So any value between 2.7477 and 3.37 would give us a radius value. Okay. And so I'm going to say, well, if the radius is 3 and the volume is 178, then what would the height of the new can be? Remember, volume equals pi r squared times the height. And we found a formula. We rearranged the formula and came up with height is equal to the volume divided by pi times the radius squared. So I know radius of 3 will give me a smaller surface area while keeping the volume at 178. And so using this formula that we also came up with the other day, I can now solve for height. Okay, so 178 okay, here we go. 178 divided by pi times 3 squared. 6.29, or about 6.3. Okay, so a radius of 3 and a height of about 6.3 are the dimensions of a can. It's one example that would have the same volume but less surface area. Okay, finally, number 7. The surface area S of R in square inches of a cylinder with a volume of 20 cubic units is a function of its radius r in units where S of r equals 2 pi r squared plus 40 divided by r. So we just used the same formula in the previous problem, except a different volume. What is the surface area of a cylinder with a volume of 20 cubic units and a radius of 4? Okay, so we already have the correct value there for a volume of 20 cubic units, and now it's telling us the radius is 4. So to answer this question, you're just finding S of 4, which means you're plugging it in. 2 times pi times 4 squared plus 40 divided by 4. Okay, and so again, I can use the calculator here. 2 pi times 4 squared plus 40 divided by 4, 110.5. So the surface area is about 110.5. Doesn't tell us the units, but they would be squared. All right, that is the end of your assignment.